right, we are now going to start talking about, okay, our rational functions. Okay, rational functions are simple functions that are the ratio of two polynomial functions. So here's a new function, f of x, which is simply one polynomial function divided by another polynomial function. Anything is possible. Okay, a quadratic over a cubic, cubic over a quadratic, a linear over a quadratic, quadratic over a linear. Any number of possibilities exist. Okay, so in general, this is how we define them. Obviously, we can't have a zero in the denominator. Okay, so we make that stipulation. The denominator q of x function cannot equal zero. Okay. Here's some familiar ones. 1 over x, one of our 7 deadly functions, okay? Um, very familiar to you. And so we can look at translations of 1 over x, which we will do very shortly, okay? 1 over x squared, another very basic rational function. With this, of course, you should surmise that the values of x are undefined at 0, much like this over here. So we're going to have that vertical asymptote as 0. But this values will always report back positively. So therefore, the graph is going to have a range of simple positive values. And there it is. I often think of this as the Atari shape, the 1 over x squared. Some continuing on, 1 over x cubed. We should surmise that that's going to look very much like 1 over x, okay? And it does, okay? It tends to flatten out. It tends to move towards the x-axis a little bit more quickly. That's the asymptote, the horizontal asymptote. Seems to be moving there a little bit more quickly, but generally the shape is the same. 1 over x4 should mimic this 1 over x squared in many ways again, although seemingly moving towards the asymptote a little bit more rapidly. Okay, so as a general rule of thumb, for any integer, for any rational function of the order 1 over x to the n, and to keep it rational, of course, the polynomial has to be, the denominator has to be a polynomial, implying that the powers have to be in positive integers. Okay, we would say this: the m behavior, that is, as the function moves towards the infinity, positive or negative, the m behavior moves towards the line y equals 0, the x-axis. All these functions will be hugging the x-axis. They'll never cross it. They'll just get closer and closer and closer. That's what we call the horizontal asymptote, and that's what asymptotic behavior means. It means you're moving towards that. Horizontal line without crossing it, but just getting closer and closer as you go further out. And again, using the notion of the calculus, we can and should be able to understand what this implies. As the values of x approach negative infinity, the function value approaches 0. Likewise, as the value of x approaches positive infinity, the function value moves towards 0. Okay. Now let's take a look at a couple rational functions. Here's one which should be looking familiar to you because it's a simple translation of 1 over x. Here's the graph, but of course we want to discuss how we get that graph. Okay. As we said, this is a translation of 1 over x. The x minus 2 is responsible for moving that 2 units to the right, and the plus 1 is responsible for moving that 1 unit up. So if we momentarily go back to our 1 over x graph, which hugged the x-axis as the vertical asymptote and the y-axis, the x-axis as the horizontal asymptote and the y-axis as the vertical, then the translation should move those axes respectively. So this is moving our vertical asymptote 2 units to the right at x equals 2, and this is pushing it up 1 unit, so the horizontal asymptote is at y equals 1. Okay, so seeing that as a translation is probably the best way of looking at that. Okay, We do speak of the horizontal asymptote as that line y equals 1, because it was the function, since it's been a translation of 1 over x, is moving up 1 and is going to move towards that horizontal line. Okay. Now the vertical asymptote, okay, is the line towards which the vertical line towards which the function moves, okay, just getting closer and closer, but never touching, never crossing, okay, and that's the x equals 2. We do note that in creating that translation, moving it up 1 and over 2, we now pick up some intercepts that we didn't have previously, okay? So to take a look at those, sorry, let's go back to that momentarily. Okay, taking a look at the intercepts, okay. The x-intercept, of course, is when y equals 0. So if you come up here, you set y equals 0. It shouldn't take a whole lot to figure out that x is equal to 1, okay. And likewise, the y-intercept is when x equals 0. So if you throw x as 0 up here, going to have negative a half plus 1 is going to give you a half. So there you pick up your intercepts that you didn't have previously, okay, with the simple 1 over x. Let's do one from scratch here. Oh, no, here's the same function, okay? We're going to talk about how this can be written in a more recognizable form. This was not a polynomial over a polynomial, which a rational function was stated to be on the first slide. So we're going to put it in that form. And putting it in that form means, of course, rewriting 1 with the common denominator. So we will do that. And then we'll combine our terms in the numerator. And here it is. So this function is identical to this function. It's just that it's in a different format, but it is verbatim the same function. Now, there are what we saw from the previous things, the things that interest us most: the horizontal asymptote, the vertical asymptote, the x-intercept, and the y-intercept. They can all be found very easily here. So let's take a look at how we can obtain them. Okay, again, this is a more traditional format of a rational function right here. Illustrating one polynomial divided by another polynomial. It's a very simple, because it's a linear function over a linear function. And of course, linear functions are, of course, polynomial functions of degree 1. All right, so taking a look at this now, okay, you'll appreciate the fact that in this form, you really don't have to do much of anything to find those crucial ingredients for graphing. The horizontal asymptote is saying, well, what happens when x gets very, 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 very large? Okay, so when x gets very, 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 very large, basically, if you take 1 from the top and 2 from the bottom, it's not going to make much of a difference. So I can, if for all intents and purposes, ignore everything but the lead-off terms, which is x over x, okay? And x over x, of course, simplifies to 1. So my horizontal asymptote just says, let's take the ratio of the highest power terms between the top and the bottom. The ratio of the highest power terms between the top and the bottom is simply x to x, which is 1, giving us our horizontal asymptote of 1. We now need the vertical asymptote. Well, the vertical asymptote is easy to determine, because it's simply the value of x for which the denominator is undefined. And this is something we've been trying to instill with you from day one. You always say, oh, in this, x can't equal 2. Well, you're exactly right. X can't equal 2, which forces the asymptote, the vertical asymptote, to occur at x equals 2. So in short, whatever causes the denominator to zero out will contribute a vertical asymptote. Okay? Next we look for the x-intercept, which occurs when y equals 0. So we go to our original function here, and this f of x, of course, is y. So if we let that equal 0, if we cross multiply, we still get x minus 2 times 0 is 0. So in short, okay, if we simply want to find the x-intercept, we will simply just let the numerator go to 0. And what makes the numerator go to 0? Well, 1. So there is my x-intercept. My y-intercept is when x equals 0. So when x equals 0, it's easy to see that I'm just going to have -1 over -2, which is going to be my y-intercept of 1/2. So there you have it. Take the ratio of the highest power terms between top and bottom. That will give you the horizontal asymptote. Determine the value of x causing a 0 to occur in the denominator. That's the vertical asymptote. Sometimes you might have 2, 3 vertical asymptotes. Sometimes you might have none. Okay, so it's just whatever offsets the denominator to 0. The x-intercept is simply saying, well, hey, what makes the numerator go to 0? Of course, here it's one term, but it could be more than one. It could be 2, 3 x-intercepts. It could be no x-intercept. Okay, so we just have to accept that in a more general form. And again, setting x equal to 0, that's the simplest one right there. It's -1 over -2, or 1/2 for the y-intercept. So let's try that with the next problem at hand. So here is the problem, and the nice thing here again is that everything is there for the picking. The horizontal, vertical asymptotes, the x-intercepts, the y-intercepts, put it all together and you got the graph. So again, the horizontal asymptote simply asks you to take the ratio of the highest power terms. So just ignore everything but the first terms. You got -3x over x, which is -3. Now remember, that's a horizontal line, y equals -3. Okay? The vertical asymptote. Well, the vertical asymptote, what makes the denominator 0? Well, -2. X plus 2 equals 0 when x equals -2. So there you have your horizontal and vertical asymptotes. Okay? What's the x-intercept? Again, the x-intercept quite easily, just determine the value of x causing the numerator to 0 out. And that, of course, is -3x plus 6 equals 0, -3x equals -6, x equals 2. And the y-intercept, again, set x equals 0. You got 6 over 2. That's simply 3. So we'll put it all together. Okay. Here we have, we're sketching in our horizontal asymptote, the line y equals -3. That's sketched in. Again, that's just a guideline. That's an asymptote where our function's moving towards that. We got the vertical asymptote at x equals -2 as shown here. And oh boy, how about that? Okay, so let's get back to that in a minute. It's annoying, but I'm not going to I'll start all over again, so we'll just come back to that. Okay, all right, bear with me a minute here. Okay, we had it all but done, and then we had a little issue there, so here we go. Okay, so here's the graph. We found all these items. Okay, we sketched in our asymptotes and our intercepts, and of course, well, the asymptotes are there as guides, and the intercepts are there as points we need to run through. So there's really not a whole lot of choice. We have to remember this is probably just a variation of 1 over x. So we're going to ride this red line, asymptote, come down, go through 2 of these points, and then head off for our blue horizontal asymptote. Likewise, over here, we're going to have the same kind of thing, but we're just going to be confined by those 2 asymptotes. And so here's the graph. Okay, here's the graph. Right there, it is. Okay, and there we have the riding those asymptote lines. Okay. The end behavior illustrating that as x moves towards infinity, the function moves towards the line -3. Okay, next moves towards -infinity, the function moves towards that horizontal asymptote of -3. So there you have it. Okay, our introduction to rational functions.